Thank you very much for the invitation. It's very nice to be back here. I was here, I think, 7 years ago or so. So I here have a list of my colleagues. I won't read all of them for you, but the experiments that I will tell you about were carried out by 2 PhD students, Didier and Olivier, and alongside with major contributions from now a former postdoc, Thomas Moire. All right. So let's start from basics. So basically, this talk is about different materials, strongly correlated materials, and maybe it's good to start out by emphasizing that most of the materials that we deal with, including the ones that we use to make this diode laser, are actually, even though they're complex, have many electrons, etc., their properties can be described by an effective single particle model. Okay, so this includes metals, insulators, semiconductors of almost all types. And so this is really nice because once we have a description based on single particle physics, then we can make good predictions and make realized devices using these predictions. But there is a smaller but a very important class of materials where the correlations between electrons become important in determining the functionality. Okay? So examples of this is high TC superconductivity, first and foremost, and also exotic forms of magnetism, one of which I'm going to tell you about. Right? And basically, these materials with strong electronic correlations are difficult to analyze. Actually, the whole field of quantum simulations was motivated by trying to understand the properties and make predictions about these strongly correlated materials. And what's more is that they exhibit rather unexpected and so-called emergent properties, such as charges that are fractionally charged. So essentially current carried by not an integer multiple of E, but E over 3. Okay? Or spin charge separation, that when we inject an electron, spin and charge degrees of freedom seem to have or can have their own life independent of each other. All right, so then the question is, this is good, it's good to understand, where do we look for? So what is the criteria that we need to have to judge if correlations effects are important? And basically, this actually is a relative simple comparison between the ratio of interaction energy to kinetic energy. So if we focus on a two-dimensional system and assume that we have charges, it doesn't have to be this way, right? But I'm going to focus on charges that interact with each other with long-range Coulomb interactions. And then the kinetic energy is the usual single particle kinetic energy. Okay, so if you do the math, you'll see that the kinetic energy of a fermionic system, the characteristic kinetic energy, scales with the density of electrons. This has to do with the Pauli exclusion statistics. And the Coulomb interaction for a characteristic separation between charges determined by the density of the charges scales as square root of density. So if you look at the ratio of these two, and this is called the RS parameter, you'll find that it's proportional to some fundamental constants. An important element is how heavy the mass of the charges are, okay, and this will become important. But but most importantly, this ratio scales as 1 over the square root of electron density. So lower the density, the stronger the effect of correlations. Even though we reduce the strength of interactions, we reduce the kinetic energy scale faster, and therefore the system becomes more prone to correlation. So what exactly I mean by this? So I will discuss the simplest experiment, simplest system, which is kind of dear to my heart because we were able to demonstrate this 4 years ago. So let's consider a Fermi liquid. So we take a semiconductor, we fill it up with electrons up to a certain density, certain Fermi wave vector, and we normally expect that the electrons will form a Fermi liquid. Okay, so which means that there's an average separation of electrons, but the electrons are translated invariant. So basically, there is no order in the system of electrons. Okay, so this is the case when the RS parameter is small. And for those of you who work in 3-5 semiconductors, RS parameter there is about unity. And so in this case, Fermi liquid description is extremely good for, let's say, densities on the order of 10 to the 11 per square centimeter. Now, if we manage to lower the electron density without hitting the wall of disorder, right? This is important. This is not in my description. So I'm going to assume a pure enough material that I can just lower the density of the carriers without having to worry about the carriers being captured in disordered potential. Then what we would observe when this RS parameter actually exceeds 35 is that electrons will find it favorable to form a crystal. This is the Wigner crystal that was predicted by Eugene Wigner 90 years ago. And basically the idea here is this, that localizing in a lattice has a kinetic energy cost, but this kinetic energy cost can be overcome by minimizing the repulsive energy by maximizing the distance between the carriers. And that happens in a triangular lattice. Okay? So this constitutes a spontaneous breaking of translation symmetry. Now, you can say that, well, we call this now a strongly correlated system. It actually allows for a relatively simple description. So the really interesting physics is actually in between. And how exactly this transition occurs, whether there are intermediate phases and so on, it's still not a completely resolved scenario or question. Okay, so this is, and please interrupt me if you have questions. So this is the setting, a simple example. We'll see more interesting examples, hopefully shortly. But the question is, the requirement for this is rather large. So RS parameter of 35, as I mentioned, in gallium arsenide, this is about unity for typical densities. So this really requires a very heavy mass of electrons before we can get to a regime where this parameter could be solved. Okay, so what do? There are actually two possibilities if RS parameter is small that the physicists have explored over the last 40, 50 years. The first one is to apply a large magnetic field. If you apply a magnetic field, you know that electrons make cyclotron orbits. So in quantum mechanics, they form lambda levels, and these lambda levels have no energy dispersion. So you have a high density of states with identical energy. And that actually satisfies this condition that effective RS could become large, even though one should not use this formulation in this case, because of the fact that there is no kinetic energy cost. The only energy scale is that of interactions. Okay, so in that sense, the system is bound to exhibit interesting correlated states. And this indeed is the reason why fractional quantum Hall states appear and have been studied as the prototypical strongly correlated system exhibiting the fractionally charged excitations. Another possibility is to use a periodic potential to create flat bands. Okay, so this one actually is also not terribly new in a way that, if we consider platforms for systems exhibiting strong correlations due to periodic potentials, periodic potentials, you can say, exist in every single solid that we are dealing with. The atoms form a periodic lattice, and then but normally the electrons in metals are very delocalized, so they kind of do not see the lattice. That's why when we describe gallium arsenide's properties, we even forget about the underlying lattice. We treat them as effective free particles with a certain effectiveness. This is not true if you have d or f shell electrons, which really like and are strongly bound to their parent atoms. So in that sense, they really do see their properties are strongly modified by the presence of the lattice, and their effective mass can be substantially larger. Okay, so that's one setting. The other setting is has become popular over the last 20 years, and that is the cold atom quantum simulators, where there are no parent atoms. So after all, you are dealing with atoms. And then you subject them to an external potential that is generated by laser fields, interfering laser fields. And so the idea that has been driving quantum simulators, as I mentioned, is that somehow this can be used to simulate what is happening there. Okay? And if your classical computers fail because of the complexity of the many-body problem, you can resort to a system of cold atoms and do a quantum simulation, just like what Richard Feynman suggested more than 40 years ago. Okay? Now, if you compare these two systems, they cannot be more different, right? If I look at the length scales, so for atoms, for real solids, the lattice length scale is like 2 angstroms or 2 to 3 angstroms. And the relevant energy scales are on the order of electron volts. So for cold atoms, the lattice length scale is determined by the optical wavelength. It's about a micron. And then the interaction energy scales are about a nano electron volt. So for this to work, of course, you have to really cool down the atoms to basically nanokelvin temperatures in order to see the quantum effects where temperature is less than the interaction energy. Okay? So, what this system offers is extreme tunability. One can tune interaction strengths, they change the potential, etc. But you can say that its functionality is as much as your computer. Right? So it's not a system which you can use as a device for some application. So these guys, on the other hand, the strongly correlated materials like ITC superconductors, have real applications that one already has, and one hopes to have more if one gets to room temperature. But their tunability is extremely poor. Okay? So basically here you see the phase diagram of a cuprate. You see that it has many interesting phases as a function of temperature and hole doping. Okay? So this means that if you have no holes in the system, it's an antiferromagnet. It's interesting, but not very, well, maybe it's useful. I shouldn't say that it's not very useful. But basically, the interesting things happen as you start introducing hole doping. Okay, then you have this pseudo gap, this strange metal tied to the D-wave superconductivity, etc. Okay, now the difficulty here is that while I can tune the atomic density and this lattice as I will, here I have very little tunability. Every line here would require a different sample. Right? The holes, the doping has to be introduced during the growth process. So you have to, in order to sort of study this phase diagram, you have to generate a large number of materials, or you have to grow a large number of materials and try them out as a function of temperature, measure their conductivity, etc. All right, so that's kind of the challenge. And now what I'm going to try to convince you is that there is actually a third way, and this is provided by the twisted van der Waals materials, which actually have length scales on the order of 10 nanometers, lattice length scales, and then energy scales on the order of 10 electron. Okay, so which means that it's still going to be a cryogenic experiment, but in the end, this is good. It's a solid state system. So when you observe, when you talk about superconductivity here, it is real superconductivity. It's not a simulation of superconductivity. All right, so let me now sort of go through why these systems are nice and important. I already made this point that in order to study the full range of strongly correlated physics, you need to be able to tune the Hall density, and this is difficult, right? Every point requires a new sample, such that we have a different so-called filling factor, that is the number of, the fraction of sites where an electron is missing. Okay? So now, how can we go around that? So one possibility, and this is this discussion from Sid Parameswaran, which I like very much. So, so we can say, well, instead of doping, can we not just use electrical gate? You know, after all, we can think about the capacitive structure, and if we apply a voltage, let's say between two plates, let's assume that their separation is 10 nanometers, but this could be 100, doesn't matter. Then I can apply a voltage of about 1 volt, okay, before the material in between starts to leak and it doesn't really work as a nice capacitor. Okay, so if I increase the distance to 100 nanometers, I can apply 10 volts. But what is really limiting here is the electric field that you can apply, which is about 0.1 volts per nanometer. Okay, so there are some devices that go up to volts per nanometer, but this is kind of the range. Now, in such a structure, if I look at the electron density, then I will, going through typical dielectric constants of about 10, what I will find is that the maximum density I can get is about 1 electron for 10 nanometers. So which tells me that if I have a lattice where the lattice period is about 10 nanometers, then I can actually control the charge density or the filling factor anywhere from 0 to 2, 3, etc. Okay, so that's the idea that in order to be able to have this electrical tunability, we need a new lattice length scale that is on the order of 10 nanometers. It doesn't have to be 10, it can be 5, but something that is at least an order of magnitude larger than the actual intrinsic lattice length scales, which is about 0.2 nanometers. Right? So now this is where the two-dimensional materials come in. So let me say a few words about them before I tell you about the 10 nanometer length scale. So these are materials which have strong covalent bonds in the plane and weak van der Waals coupling between the layers. So they're called layered materials, and this has a very important consequence that you can actually use Scotch tape or some variant of it to peel off material down to a monolayer level. Okay, so and this was, as you know, was first done for graphene by Andre Geim and Kostya Novoselov. And the idea is that you can really, with relatively high success rate, go to a monolayer of, say, graphene, which is a semi-metal. You can also do the same for about 5,000 different materials, which include semiconductors. These are the transition metal dichalcogenides, which I will come back to. You can do it for hexagonal boron nitride, which is one of the best insulators you can imagine, which allows for this gate tunability that stops current while you're applying large electric fields. And you can actually take these and stack them on top of each other, and you can actually get new functionalities. For example, you can take a superconducting layer and put a ferromagnetic layer on top and see how this modifies the properties. Okay? Now, that's fine. That's actually what the community has been dealing with for like 15 years. But what has been realized by Alan MacDonald and Bistritzer about 14 years ago is that there is a lot more you can do if you do your stacking of two monolayers with the small twist angle. Okay? And this is a picture of what happens. So two hexagonal lattices, it could be graphene or it could be anything, or honeycomb lattices. You see that when there is a twist angle, you see a new periodic structure appearing in the system. And the period of this new super lattice is simply given by the underlying lattice constant divided by the twist angle. So if you have a twist angle on the order of 1 degree, you do get a moire period on the order of 10 nanometers. Okay? And this is basically the idea why two-dimensional materials are so nice, because you do not have to worry about whether these are compatible measurements, similar lattice constants, etc. Although this particular twisting idea works extremely well if they have the same lattice constant, if they have the same material. But you can actually take them, and while stacking, you can introduce the angle to create your length scale. Now, the first experiment on this was by Pablo Jarillo Herrero at MIT, where what he showed, following McDonald's proposal, is something really remarkable. He starts from graphene, which has massless electrons, the worst you can imagine in some sense, because they're basically completely linear dispersion. And when you go to a twist angle of about 1 degree, 1.08, then you find that there is, actually this is the remnant of the linear dispersion, there's a completely flat band appearing in between, which is layer hydrodynamics between the two. And then when they did the transport measurements, you see the similarity of this phase diagram to what I showed for the Cook rates, the temperature versus the carrier density. And now the carrier density, actually here it's only holes, but electrons, I forgot, I think it's electrons. But here you can actually do it for both electrons and holes. You can move the chemical potential up or down the charge neutrality point. And what you see is that you go from insulating states to superconducting states, etc. Right? So almost exactly the same kind of phenomenology or phases that you observe in proteins. All right, so this was the first story in 2018. Then came in 2020 results on twisted transition metal type hydrogenides. Now we're dealing with semiconducting materials which have a reasonably high effective mass for electrons and holes. And in this case, you don't need a particular angle. All angles are good, just the angle can be used to change the periodicity. Okay? And when you do your DFT calculations, you find that this system also exhibits nice and relatively flat bands. And in these relatively flat bands, basically what you need to compare the interaction energy to is interaction energy at the lattice spacing to the bandwidth. Okay? And here in this example, the bandwidth is about 10 millielectron volts. In the sample that I'm going to show you in twisted molybdenum, if there's a remarkable effect at one twist angle where the bandwidth with interactions can go actually down to millielectron volts according to calculations. Okay, so in that sense, the kinetic energy can become completely negligible compared to interaction energies, which are on the order of 50 millielectron volts. All right, so semiconducting materials also allow for optical spectroscopy, which is what we use. I here list the difficulty as making good electrical contacts. This is now more or less overcome by several groups that you can actually also do nice transport measurements and see, let's say, conductance resistances down to a few ohm. Okay, so that's very neat. All right, so basically what I'm going to tell you today is more the quantum magnetism of these correlated electrons inside structures and their optical properties. All right, so this is the outline. So I will, I don't know if you have any questions. This was a long introduction, but that's what I was asked to do. So I will start out with trying to show you how we can use optics as a tool for investigating ground state electronic and magnetic properties. And actually for magnetic properties, it's probably, I would argue, it's better than the transport measurements. And then in the second part, I'll tell you about one interesting result when we have topologically trivial moire bands. So these are called moire bands, by the way. Then we observe this effect called kinetic magnetism. That is magnetic correlations between electrons that arise not from exchange interactions, but rather from considerations that are related to minimization of kinetic energy. And then in the latter part, I will tell you how we can use optical orientation or optical control of Chern number of topological sets. All right, so now I told you that the material of interest for us is transition metal like alcogenite. Now I told you about 5,000 layered materials. I don't know the number, but there are probably tens of transition metal like alcogenite in this system. Some of them are superconducting, some of them are charge density waves. We'll be interested in this subclass, which is semiconductor. Okay, so if you look at it from afar, they have a honeycomb lattice structure where the inversion symmetry is broken because A sites consist of a metal atom, say molybdenum, and B sites would consist of two chalcogen atoms. Here in the first part, this will be selenite, in the latter part, it will be telluride. All right, so what is special about these materials? They're in the monolayer limit, they're direct band gap semiconductors, or multi-ditelluride, even in bilayer, they're direct band gap semiconductors. This will become very interesting. And what is important is that the band minima are at these high symmetry points of the Burgoyne zone, the K and minus K points, which are the time reversal in their symmetric counterparts of each other. So you can think of it this way: if you consider an electron in K valley, this is an electron that rotates, say, in the counterclockwise direction between different sites. In minus K valley, it rotates in the clockwise direction. So, but the main point is that these guys, the momenta here, the large momenta is the magnitude of the momenta associated with this circular moment. Now, because of this, that the optical selection rules tell us that, say, in K valley, we can do excitations using sigma plus light, and in minus K valley, we can do it with sigma minus light. And because of the fact that the electron and hole interacts, this is pretty much true for all semiconductors. Here it's even more true, I'll come to that, that when we do an optical excitation, the electron binds to the hole that it leaves behind and forms an exciton. So therefore, if I shine sigma minus light, I form an exciton in the minus K value and vice versa. Okay? And this is independent of the spin. So spin actually for the lowest energy and conduction band and higher energy valence band, it's tagged to the valley. So in K valley, it's spin up, minus K valley, spin down. They're higher line spin states, but the optical selection rules are the same. It's determined not by the spin naturally, but by the circulation of the electrons. Now, I told you about the exciton. So in gallium arsenide, the exciton Bohr radius is 10 nanometer because of the large dielectric screening, light mass. Here it's about, the Bohr radius is 1 nanometer. So interactions are substantially stronger in this material system. The binding energy, even with dielectric encapsulation, is about 230 millielectron. So these are really tightly bound objects. And this will become very important for us because I will say that when I absorb a photon, I generate this tightly bound exciton, which is a polarizable object, and it will interact with electrons or holes without losing its excitonic character. Okay? But these interactions will then modify the spectrum and tell us information about what's happening with the electron. That's the basic idea. Okay. But before that, let me say that sort of how we do the measurements. So our standard tool is resonant reflection. So we basically take this material, it's not standing in free space, it's encapsulated between boron nitride to make the surfaces clean. We shine light, and then we look at what gets reflected as a function of frequency. So the simplest possible spectroscopy, and most of what I show will actually be done with white light. So basically we take an incoherent light source, sometimes we filter it down, and then we look at how different frequencies get reflected. Okay? And so one point that I think I talked about this 7 years ago when I was here, I was excited about it at the time, that these are actually materials, if you hit them in excitonic resonance, they're atomically thin mirrors. So they can reflect a very large fraction of the incident light at the exciton resonance. Okay? So this is not a typical experimental scenario. but you would routinely get 70% reflection, and the best reported from Harvard is 85%. Okay, now that's not so important. What is important is what do we see as we tune our white light source or laser. What you see is that there is some background reflection coming from all the dielectric interfaces like air to HBM and so on. And when you hit the exciton resonance, the reflection is maximum, right? But if the background reflection is also important, and it can be given that the dielectric constants are sizable, then you'll have this interference pattern more of a dispersive one. Right? So that's the standard scenario. So let's see how it looks in a real experiment. So this is a simple device where you have molybdenum sandwiched between hexagonal boron nitride, which I use the acronym HBN. So this is the insulating layer. And then I have a top gate and a bottom gate, which is a graphene. So I shine light from top and look at reflection. Graphene allows us to inject carriers. So these are the electrostatic gates that I mentioned to you, right? That allows us to control the charge and density. But they absorb, if it's graphene, it's 3% of the light is absorbed in every time. So it doesn't reduce the efficiency of the optical. And this is how the device looks like with the contacts. So it's all low-tech device fabrication. All right, so this is then how things look like. So this is the gate voltage. So for a certain gate voltage range, the semiconductor is charge neutral. There are no charges injected because of the low voltage that is applied. The chemical potential is inside the gap. And then when you tune your light source, you see this resonance. And if I take a line cut, you see that has this dispersive line shape. This is our excitonic resonance. Okay? This is not the best. The peak reflection here is 2. The best we can get by suppressing background reflection is 40. But that's not really so important. What is really important is what happens when we inject carriers into the system. So when the carriers are in, you see that 2 things happen. The excitonic resonance broadens and bullshits, loses strength. And there's a new resonance appearing at a lower energy that is directly linked to the interaction between excitons and the free carriers. So how do we understand this? So basically we start out now no longer in a neutral system. The initial state of our system is electrons in some state. In this case, this is supposed to describe a Fermi liquid, but it could also be a liquid crystal. So this is where we start. Then we send a photon, and once the photon is absorbed, we generate an exciton, just like I mentioned to you. But this is the exciton in the presence of the Fermi sea is not an eigenstate anymore because excitons interact with the electrons. So, and this interaction actually leads to formation of a bound state called trion if the exciton and electron are in opposite values. Okay? So now that there is this possibility and there is this interaction, my cheapest guess for what the eigenstates are would be a superposition of a bare exciton sitting on these electrons together with the collective excitation and the dying diode of trions to get, that is formed, that the exciton forms with any one of the electrons. So it's a collective trion-like excitation. And this superposition is what we refer to as the attractive polaron. It is this resonance that appears. The repulsive polaron is the orthogonal resonance to this. So the excitonic weight is distributed in between the two. Now, very important, and this I will show you shortly, is that the oscillator strength of this resonance, if I integrate the area underneath, is directly proportional. This is an exact expression, by the way, within this shaded image. And it's directly proportional to the electron density in the opposite value. That is, if I look at sigma plus attractive polaron, it's proportional to the density of electrons in the sigma minus value. So how do I see this? We go to a very large magnetic fields. At these large magnetic fields, we inject electrons and they remain validly polarized because G factor is something like 4. okay? Which means that up to about 10 to the 12, all my electrons will go to the K minus value. Now, if I inject my exciton in K plus value with sigma plus light, I see this nice attractive polaron and the repulsive polaron formation. But if I use sigma minus light, then I see my exciton that is still blue shifting. There's some interaction with the electrons, but there is no bound state and there is no attractive polaron resonance. Okay? Now, if I didn't go up to such a high field, then, say in this case for Tesla, there will be some electrons in the other valley. Then I see the attractive polaron in both valleys. And now, what I can do is I can look at, integrate, find out the area under these transitions. For that, I need to do a transfer matrix calculation. But when I determine the oscillator strength of the two polarizations, if I normalize it, that directly gives me the polarization, degree of polarization. So it's a quantitative measure of the degree of spin polarization in the system, irrespective of the magnet. Okay, so this is our tool. This is why this resonance is so useful in evaluating the magnetic properties. So now the magnetic properties of the monolayer is not so interesting. So we now consider in this second part a moire structure. So this moire structure is a bit different than what I showed you before. This has it's a heterobilayer with the lattice constants being different by 4%. So in usual MB growth, this would be a disaster. You'll have many defects, etc. But in 2D materials, it's something to celebrate, even without twisting. The fact that lattice constants are different results in this moire period form. Now you cannot have very small moire periods. The smallest you can have is 8 nanometers determined by the lattice structure. Okay, but that's then the structure, molybdenum, tungsten disulfide. This is for X-verse, a type 1 alignment. So all the optical properties remain the same. It's just that now electrons and excitons in molybdenum are subject to a moire potential. All right. So this is then the sketch. It's a type 1 alignment. As I said, I generate excitons here, and I will be doping electrons in the same way. Electrons are subject to this very deep potential, and they sit at sites where the two metal atoms are on top. So the depth of peak to peak of this potential is, according to DFT, 60 milli-electron volts. Hopping is 1 milli-electron volt, but our experiment strongly contradicts that statement. The on-site repulsion is relatively independent and of the potential parameters. It's about 120 milli-electron. So it's basically a very strongly interacting system. Doesn't really fulfill a Fermi-Hubbard model, right? I mean, these two numbers tell you that you cannot really expect that there will be a single band and putting two electrons, they will just sit on the same orbit. But that again is a side point for us. So this is the spectrum. So now the spectrum is much richer. So even in charge neutrality, there are additional resonances because exciton center of mass motion is also subject to a potential. But I'm mainly interested in this low energy resonance. This is what I would call the moire attractive polaron. So the counterpart of what I have shown you in the presence of a moire potential. Okay, it's weaker. That's why we multiply by a factor of 5. But this is what we're going to deal with because we're interested in magnetic properties. And for future reference, even though time is running out, there you see at nucleus 2, twice filling and thrice filling of the lattice, there are these cusps. This is a very generic signature of an incompressible state in the system. Okay, I'll come back to that, and this is what many groups have used. So again, we're looking at this moire attractive polaron. And at zero field, so this is sigma plus and sigma minus, exactly overlap, which is not surprising, so there is no spontaneous magnetization. If I apply a finite magnetic field, I find that their areas differ. And from this, as I already explained before, I can determine the degree of spin polarization. Now I can measure this as a function of the applied magnetic field, and the derivative gives me the spin susceptibility. And from the spin susceptibility, I can tell, particularly as a function of temperature, I can tell if the system behaves, the electrons are non-interacting, then their susceptibility will scale as 1 over T, or if they're interacting and have ferromagnetic correlations, they will have a positive Curie-Weiss temperature, which is kind of related to Curie temperature, and if it will be negative if the correlations are anti-ferromagnetic. All right, so before keeping the story too long, what we find is that at mu equals 1, and for a large filling factor range, let's look at this one, from 1 to about 0.5, we find this almost exactly blue curve, which is the paramagnetic spin susceptibility. Of course, with large enough magnetic field, it saturates because we polarize. And then when we inject additional electrons, when our doping is more than 1, then some sites have doublons, 2 electrons, then we see that the spin susceptibility is dramatically increased. And this is what you see here. Beyond mu equals 1, there is a jump in spin susceptibility that becomes stronger as you reduce the temperature. Right? So this is normalized with respect to mu equals 1 temperature. All right, so this is basically telling us that the system is not magnetic normally when it's in a mod state, nothing interesting, and things become really interesting, magnetically speaking, when I have some free carriers. So it's kind of an itinerant ferromagnetism that shows up. And this part I would like you to discard because we know why you have these anti-ferromagnetic correlations here because of light-induced depolarization. And this will also be related to the second part. This part I also did not mention, this we do not understand. Why beyond mu equals 1/2, where we have a Van Hose singularity, why there is anti-ferromagnetic correlation. So this, we thought about it in models, but we don't explain. So now let me tell you why we think we see the physics we are seeing. So for mu equals 1, the standard expectation, and actually that was ours, was that the system should form a 120-degree anti-ferromagnetic Neal state. Right? That's what you would read in textbooks, etc. But if you do the numbers here, the super exchange interaction is almost 0 because U is so large. Right? So for the temperature ranges that we are measuring, which is down to 150 millikelvin, there is no way we will see any deviation from ferromagnetic. So in that sense, even if there is some anti-ferromagnetic correlations, we cannot say. Okay? So if mu is larger than 1, however, the physics can be very different. Now, you can actually have a so-called Nadolka ferromagnetism proposed about 60 years ago by Nadolka. And the idea here is this, that think about this case when on-site repulsion is very large, so exchange is negligible, and so when we introduce extra electrons, of course, we need to provide this extra energy. And then the only relevant energy scale is kinetic energy. So how can this doublon, this doubly occupied site, minimize its energy? It would do so by completely delocalizing over the whole system. Now, that would mean that different paths for this doublon hopping onto neighboring sites have to interfere constructively. Right? This is only possible if all the spins are pointing in the same way. Right? So if this spin were pointing down, then basically hopping from top and hopping from the bottom will leave a different final state and the interference will be imperfect. So this is the idea of kinetic magnetism, that to minimize the kinetic energy, it is favorable to polarize the spins because there is no other energy scale. The anti-ferromagnetic interactions are so weak that you do not have to worry about. Okay? So this is the picture. So given time, I'm not sure if I should tell you, there is actually also very interesting anti-ferromagnetic physics expected as hole doping. We don't see it, and we have some idea as to why this should be, because of the strong interactions, we modify the moire potential beyond mu equals 1. So we basically have a Hartree fork moire potential. So I just want to say that I forgot to point it out, that we have this correlations increase, and then there's a dip at 4 turns. We believe that what's happening here is that the doublons form a Wigner crystal. And when they form a Wigner crystal, then basically the magnetic correlations are gone because we no longer have an equivalent doubling system. Okay? It's not perfect. Normally this should go down to unity, but that's due to moire disorder in the system. We observe a micron-sized spot, but the length scales, the lattice length scales are not identical within this, even within this. All right, and we can control the magnetic correlations electrically. This one's also lined up. And this, again, shows you that by applying the large electric field and hybridizing the 2 conduction bands, we can actually kill the magnetic correlations. So that's now, the third topic, maybe I have like 5-10 minutes. So now let's take a step back and 5 minutes. So, you know, if you look at your colleagues and condensed matter physics, you know, there are some very popular topics that make our lives interesting. So these are strong correlations, what I talked about. Topology, frustration I talked about, but topology has become extremely interesting and popular over the last 20 years. And then another topic is non-equilibrium dynamics or laser-driven floppy systems. So what would sit in the middle of these would be if we discuss or realize optical control of topological organisms. This is what I want to show you briefly. So here, my moire device is different. It's a homobilayer twisted molydipelaran, which Shalom Shu kindly provided us. This is how the device looks like. And now what is special in the system is that the holes we'll be dealing with hole doping will not be staying only in one layer, right? So there is tunnel coupling between the 2 layers, and the holes are layer hybridized. So basically there are these sort of XM and XI, so these are high symmetry points of the Brillouin zone, of the moire Brillouin zone. And basically here the hole is more likely to be in the top layer, here it's more likely to be in the bottom layer, but it's the actual hole band is in a superposition of these. So it's a honeycomb lattice structure. And what we have now is not only direct hopping between sites, which is in this case much larger, but you can also hop through intermediate sites. Okay, so you can actually use sites for tunneling, and then you have a second hopping channel. And these hoppings have a different phase with respect to each other, so they can actually destructively interfere, and this is how you can imagine the band flatness appearing in the system. Okay, so much for that. So if the system is charge neutral, again, the story is almost the same. So we have sigma plus and sigma minus excitations, the Fermi energy is in the middle. The excitons are strongly bound, not as strong as molybdenite, but it's about still 200. And there is no net moire for excitons because exciton binding is so strong that even if you have moire bands, it averages out. All right, so what happens is that when you hold off the system, then we spontaneously magnetize the system, and this is what I'm going to show you. So when the Fermi energy is pushed into the valence band, all the holes for a large filling factor regime occupy one valley spontaneously. This is energetically favorable, and the way to understand this, at least I understand it, is direct exchange. Right? So we know that exchange favors polarization. That's Hund's rule, right? And why electrons are spin polarized in let's say, carbon and nitrogen, etc. Right? But here, this is enhanced compared to other systems because of the fact that the bands are topological, have a finite Chern number, which means that they cannot be exponentially localized. They really cannot avoid each other if they have a different spin. So therefore, the exchange effect becomes more important. All right, so now Why do I say that these are topological Chern bands? So this is an experiment of photoluminescence, which I haven't shown before, which was first done by Xiaodong Xu 2 years ago. So this is photoluminescence as a function of doping. At 2/3, there is a cusp, and at nu equals 1, there is a cusp. I told you that these are associated with incompressible states. What is important, though, is that if it's a trivial incompressible state, if you apply a magnetic field, this will remain exactly at this density. Not so for topological states. The topological states, they follow the Streda formula, which tells you that as you increase the magnetic field, there should be a shift increase in the density that is needed to reach that particular Chern insulator state. And we follow this with magnetic field, and in these you find that the slope here is 0.65, here it's 1.07, which is most likely due to the fact that we don't have as well-defined cusp as that in this one. So this is a remarkable state, right? In the sense that it's a topologically ordered state showing up at zero magnetic field, right? It's counterpart of fractional quantum positives. Okay, so let me just skip over this spectra. We will again use the attractive polon resonance to study sort of how the magnetization or value polarization changes. I just want to show here that I really went through two. So basically, this is sigma plus. Attractive polon is strong here. There is nothing, right? So this again is telling us that everything is value polarized. All right. So now, if you do a magnetic field scan, instead of measuring the spin susceptibility, what we see is hysteresis, because we're now working at temperatures where the system becomes magnetic, and therefore we have this hysteresis curve. This is at -2/3. And this is at low power, and you see that we did the experiment when we probe optically, we use sigma plus, sigma minus, or linearly polarized, like nothing different. Okay? Then we increased the power, and we found something remarkable, that if we use 110 nanowatts and linearly polarized, we kill the hysteresis. So basically the system magnetization is determined by the magnetic field, and it basically has a sharp increase. But if we apply sigma plus or sigma minus, we again don't have hysteresis, but we make sure that we can change the value polarization by using the degree of circular polarization. Around 0 Tesla, that sigma plus leads to a Chern number of -2/3, and a sigma minus leads to minus k value polarization and Chern number of 2/3. Okay? And this again, we looked at the power dependence. We first initialized using magnetic field and tuned the magnetic field to 0, and the C equals 2/3 state. And with sigma plus, we were able to split it completely to C equals -2/3. With sigma minus, nothing changed. And this is the range over which, the doping range over which this works, almost covering exactly the magnetic field. All right, so I will not go through the mechanism. I just want to tell you, one future-looking thing that normally you measure edge states, conductance of edge states in quantum Hall systems. So what we are showing is that we can actually define edge states optically by exciting with the certain radiation field profile. We can define regions of different Chern numbers and which exhibit co-propagating edge modes in the system. All right, so this is kind of an output, and thank you for it.
Okay, so are there any questions for Atash?
They're not.
So I'll help you. You didn't touch upon the possible multiplier AC, or
yeah. No. So basically, there is some indication of. I should be careful here. I mean, we do see that beyond nu equals 1, that when we use the displacement field axis, so this axis that I did not discuss so much about, you see that when we change the displacement field, we basically kill the layer hybridization. So this set mu equals 1. If I go to mu equals 1 plus 2, or 1.2, right? What we see is that there are these two attractive Coulomb resonances associated with excitons in either layer. We find that the extra holes immediately flip to the other layer, not valley, as we change the displacement. So it looks like ferroelectricity for these excess carriers, but we haven't seen hysteresis yet. We haven't studied. So that's why I said possible multi-ferroicity, because the system is ferromagnetic, right? It's still valley polarized, and then it seems like at least for excess carriers, there is a tendency to layer polarize.
Yes, so I have a few questions actually. So when it comes to the super lattices, do you need to have the same lattice structure for the different monolayers, or can you have a cubic lattice and then a hexagonal lattice?
Yeah, excellent question. So I would expect that if the lattice structure is different, then the physics would be very different. I mean, in principle, I should say that these are kind of quasi-crystals, right? Because except for certain matching angles, you would not have true periodicity. And the idea here is that if the angle is small, it's almost periodic. But there are also experiments in bi-layers that Pablo is doing nowadays, which really explore the, it's in his case it's moire of moire, right? And there he sees signatures of quasi-crystalline structure. So this I do not know. I mean, that's the short answer. I would expect that quasi-crystalline properties would become very important, because the lattice structures being different most likely sort of would make it impossible to have this reproducing structures.
Okay, another question is how do you know it's a trion and not like a bi-exciton? Tri-exciton, like how?
Yeah, so in this case it's easy because it's a trion because we have very low density of excitons, and the strength of this attractive Coulomb resonance, or in photoluminescence trion, it increases linearly with the exciton density, whereas bi-exciton should increase quite rapidly. And we see bi-excitons of interlayer excitons and intralayer excitons, so bound state of absorptions. But that's a different animal that I have.
Yeah. Okay, and one last question. Yeah. What experimental techniques have you used mainly to investigate and get these graphs?
Yeah, so as I tried to mention, it's mostly white light reflection. Right? So that's the remarkable thing, that you have to do polarization resolved measurements, and in some cases, for example, in this polarization experiments, we had to filter out such that we only excite the attractive Coulomb resonance with the white light. But this one is taken with broadband white light, right? Such that we get the whole spectrum. But at this point, it's relatively simple reflection spectroscopy. So the difficulty is more combining it with low temperature experiments.
Any more questions, Prakash?
Hello. I just want to ask how hard is it to synthesize these kind of samples, because these properties are material based, and
yeah.
So how hard?
It's not easy. I mean, the last set is twisted molybdenum. We haven't tried it yet because, as I said, Shadon kindly agreed to provide us. Now, with the other sample, let's say that this device that we investigated here, we basically made 4 attempts, and 2 of them worked nicely, exhibited the moire lattice structure. So I think that's a relatively low rate for us, so it doesn't speak so well for our abilities, because here it should be higher, but it's never 100%. So you see the main problem with moire structure, so if you, again, different levels, right? The single layer structures, the success rate is essentially 90%. So you have to have something going wrong with the contacts that we usually use graphene, could slid away, and then we cannot contact, and that's a failed device. Right? So once you go to moire, the main difficulty is whether you can actually reach the targeted twist angle. And then with how much the twist angle varies over the sample. This is particularly challenging for graphene because they need the magic angle. Here there is more flexibility, but then the material disorder is worse. So I don't know if it explains the 50%, but yeah, that's.
And do you also have problems with like substrate, if you use different kind of substrate?
Yeah, we've been using the same substrate now for a long time, the silicon dioxide. But we did have actually devices with which were transferred onto a DDR layer to do polaritons, and it works well. But these were monolayer devices.
Okay, last question if there is one.
Yes, so you said that there is no net moire effect for excitons, but is that in this specific structure? And can you say why in this specific structure you don't have
Yes. So basically, so that's something special for R stacking. And what happens is, I didn't have time to go through that, but I told you that. I should use this one, right? So let's say for the top layer, the minima, the maxima for the valence band, right? So minima for holes is at the MX sites. And for the bottom layer, it's opposite. It's at the XM sites. Now, here you have the maxima of valence band, minimum for holes, and there's also maxima for the conduction band. So that's actually a maximum for the electrons. So it's almost like what you would have in an electrostatic scenario, right? If you have an electrostatic potential that is varying spatially, then electrons and holes would see exactly the opposite potential, because one will be attracted, the other one will be repelled by. And then if you move around, you'll have gradients, so there will be a second order moire effect that goes as these electric field squares, but the average potential seen by the exciton will be identical. And that's, I believe, what's happening here, and the spectra also doesn't show any additional moire excitons, unlike the heterobilayer structures.
All right, so let's thank Atash again.